All right, horizontal coordinate systems. The common one is the Cartesian system. Describes locations in three-dimensional space, x, y, and z. X-axis is to the east, y is to the north, and z points into space, straight up. Compass directions do not mean much for the balance of forces on an air partial. This magnetic compass is, you're always 10 degrees off. It's like wind directions. You know, true north and true north, you're about 10 degrees off in most places. When, like a jet stream, what forces are acting upon, because you think of it on the horizontal, you're at one layer, and what forces are acting upon that air partial at that layer. So that's what matters in the coordinate system. So do you have upward vertical motion under the jet, downward vertical motion under the jet? What quadrant of a jet max are you in? Once you break down that jet core into three-dimensional, then you can pull the XYZ axis, and then you can pull the XYZ axis, and then you can say, you know, do I have upper level divergence in this sector of the jet max? Do I have downward vertical motion? You know, upper level convergence, divergence in which sector of the jet max? That's going to give you the answer based on these axes. You know, you're not really going to use those, but you're going to, once you get the, I don't know if I got any pictures. I don't. So once you get the picture of a jet max and you understand the XYZ axis on that jet max, then that's when you're going to see what areas of the jet max, that core, is going to increase upward vertical motion or decrease upward vertical motion, or upper level divergence, upper level convergence. So that's, we'll get into that. We'll break that jet stream down, the jet stream max. I think I have it on my website somewhere, so meteorology101.com. But the horizontal coordinate system is the typical Cartesian system. Pretty much all you need to really get out of this thing, X, Y, and Z. Vertical coordinate systems, aircraft flying at 30,000 feet, is referring to a height coordinate system. In this system, Z points upward. Meteorologists frequently use the pressure coordinate system, which describes heights in terms of pressure, millibar or hectopascal. So 500 millibars, like I said, a 500 millibar chart, that's our height chart. Pressure coordinate systems are also used. 500 millibar, the height at which a barometer would have to ascend to give a reading at 500 millibars. So a reading of 500 millibars. So 500 millibar pressure, what height do you have to take that to? I guess it's a, so the 500 millibar constant height chart, that's so what height would you have to take a barometer to get that, to get the 500 millibar reading? How high is that 500 millibar level? Because it's variable on a 500 millibar chart. When you throw the contours on there, they're curved. You have troughs and ridges, so some areas are lower than others on the 500 millibar level. So usually around 18,000 feet above sea level, that's kind of the standard atmosphere. It's about 18,289 feet to be exact, and that's above sea level. That is your 500 millibar standard height. So here's your standard heights. Okay, 1,000 millibars, approximately, that is approximately 364 feet. There it is right there. 111 meters. 850, 1,475 meters, or 4,781 feet, roughly 5,000 feet. 798, just under 10,000 feet. 500 millibars, just over 18,000, and 300, just right around 30,000. So that's the easiest one to remember. And then you can go 250 millibars, which is 33,999 feet. 200 millibars, 38,662 feet. So these are your standard levels of the atmosphere, the mandatory levels. Any balloon that's let go, they're going to give you winds, temperature, dew points, everything at these layers, no matter what. radiosonde that they let go with the balloon, that is what that's designed to do, is send back readings at these levels no matter what. Alright, so vertical coordinate system, the height where it occurs forms an imaginary pressure surface. The height varies according to the atmospheric density below that particular point. So the lower the density, the higher the height, so that's how it varies. These readings are mapped out as lines of equal height on weather charts known as contours. That's what we talked about, was those constant height charts, the contour gradient, on the upper air charts. It's contour, it's a pressure gradient on the surface chart. So areas of higher heights indicates the heights of the pressure level is unusually high, and high pressure warm atmosphere below. Now you can go, high pressure can be cold, dense, and low, like low heights, because it's cold and dense, so it compresses down for lower heights. So your low pressure can actually, the warm air rising up and just building up like that heat low over Texas. We've seen that temperature pocket in the upper level, so you would definitely have a little bit higher heights there just because of the warm pressure bringing all that up. Our Cartesian system of Z is replaced with a P, and the P points downward, not upward. That's on the vertical. Like I said, I don't think I have a picture of this one though. Weather systems and circulations are described in terms of their scale. Okay, so we're going weather system scales. Now, we're getting into a little bit better stuff now. We're past that physics stuff. It gets a little dry. Like I said, just understand that like cold air is more dense than warm air. Our atmosphere is naturally unstable because we have cold air over warm air. Cold air wants to sink. Warm air wants to rise. So if you're got higher pressure, colder air, more dense, pushing down on an area, you have higher pressure because you have more density, and you're not increasing the volume. You just have an area of high pressure over one area, and it's pretty much centered over a state. I mean, it is a pretty big area, but you got higher pressure in the center of that high, and then low pressure in the center of the low. Alright, so our scales, weather system scales, when we measure on planetary scale, synoptic scale, sub-synoptic scale, mesoscale, and a microscale. Okay, so the planetary scale, 10,000 kilometers or greater. Pretty much, this is mapped down there as a picture of the northern hemisphere. It's hard to tell. Weather life cycles for weeks or months. All those long wave troughs just keep going around. You get like you talk about the polar vortex, the troughs going around that pressure system in the right over the poles. So general circulation of cold air at the poles, and then a broad system of westerly flow around the globe. So you have a westerly flow constantly going around the globe. Synoptic scale, 1,000 to 10,000 kilometers. Weather life cycles days to weeks. So you can pretty much say, okay, it takes a few days for a frontal system to move across the United States. So now you're on the synoptic scale. Encompasses baroclinic waves, frontal systems, and long waves. So baroclinic wave is, say, like thermal advection. This one doesn't show a whole lot of thermal advection. So right here you have some weak thermal advection right in that area. So that would be a baroclinic wave. So you have a baroclinic ridge in this area. Now, then like we said, frontal systems, it takes a few days for fronts to move across the United States. So frontal systems, obviously, and then long waves. So a long wave would be maybe a little bit longer than this, but yeah, half the United States. I mean, you could almost call that a long wave. What you typically your long wave's about you look at the jet stream and where your long wave, where that trough is in the jet or the ridge is in the jet, that's your long waves. So that's 1 to 10,000, pretty much across the United States. Sub-Synoptic Scale is 100 kilometers to 1,000 kilometers. Weather life cycles hours or days. So now you're zooming in on a certain quadrant of the United States, certain area. Okay, we got a low pressure system over Kansas. Now, that low pressure system is only going to hang out there, for maybe a couple days or something, or a day. It's going to continuously move to the northeast, depending on where the jet stream is, if the mid-level flow, how it's going to steer that low, where it's putting it at. If you don't have a high pressure system or a ridge coming in, a subtropical ridge coming and blocking it or anything like that, you don't have a blocking pattern, then this low pressure system will kick out of there within a day or two. So it's hours to days. It encompasses squall lines, tropical cyclones, and short waves. So even a tropical cyclone, you have that hurricane, even off of the east coast, that's a very small area. So you're still on the sub-synoptic scale. Okay, so the mesoscale, 10 to 100 kilometers. Now we're down onto the radar range. Weather life cycles minutes to hours. This frontal system or this squall line or convective weather is moving out. It's moving fairly quickly. Within a few radar shots, that's gone. So minutes to hours. Includes thunderstorms, coastal fronts, dry lines, or graphic effects. So if you have a mountain range, then you'll have an area, say a thunderstorm that moves along into that mountain range. You can go up that range, give you your lift, rain itself out. Create the thunderstorms and rain on the windward side of the mountains. So you have orographic effects. That's that small area. Like I said, pretty much minutes. This is minutes to hours. Then you have the microscale. 10 kilometers or less. Weather life cycle is seconds to minutes. So if you look at this, you can actually watch, not on this screen, but if you watch your clouds, you can actually see them building up or dissipating. So that's your microscale. Includes turbulent small clouds, tornadoes, dust devils, mountain waves. So you get a wind hit a mountain, create a mountain wave. Tornado, that's microscale. That's pinpoint exactly where a tornado is going to land. You don't know. You get the general area, and then you start watching stuff on radar, and you can get to it. Dust devils, there and gone. Small clouds, like I said, you just watch these clouds. You can watch them build and watch them dissipate. Just sitting there watching clouds, all day, just see the microscale happening right in front of you. All right, atmospheric structure. We talked before about we are in the troposphere. We're at the lowest level of the atmosphere, and typically temperature decreases with height. You get to the transition between the troposphere and the stratosphere. That is your tropopause. No temperature change with height. Get into the stratosphere for the second layer, and then you get into the stratopause, and then you get into the mesosphere. Now you do have another decrease in temperature with height. That is an unstable layer, but there's really no moisture in that area. The density, there's no density at all, hardly. It's the molecules can't even hardly touch each other, so you're pretty much, no weather exists in that area. You do have some few clouds that can happen in that area, but you really can't see them. Then mesopause is the transition up into the thermosphere, and then the thermosphere is what protects us, and then that's a major inversion. Temperature increases with height, and then that pretty much caps the atmosphere. Now you have the exosphere and a couple other layers, but we don't even really need to worry about all those. We're in the troposphere. All we need to do is worry about that one. That's where all the weather occurs, and that's what we're looking to analyze, diagnose, and forecast. All right, so planetary boundary layer we also have in the free atmosphere. So your planetary boundary layer is pretty much on the surface. Anywhere there's friction is your planetary boundary layer. Once you get to the level where there's no friction, that is your free atmosphere. Now the atmosphere is free to do whatever it wants. There's no friction in interfering with it. All right, so troposphere, lowest layer in the atmosphere, contains nearly all the Earth's weather. Temperature decreases with height. Top of the troposphere is a tropopause, ranges from 4 miles in polar regions to 11 miles in tropical regions. So our atmosphere is not perfectly round around the Earth. It is lower in the lower heights of the northern of the poles, and then higher at the equator. So you're 11 miles thick at the equator, 4 miles thick at the poles. Okay, so temperature decreases with height, unstable environment, cold over warm. Top of the troposphere is the tropopause. The one thing you need to know about that is like about, say, 50, 60,000 feet, depending on where the tropopause is. Upward vertical motion, get an updraft in a thunderstorm, can push all the way to that layer, take that moisture with it, and push it and shoot up into the tropopause. Even though it's not a temperature change with height, it can push through that, and then you'll have those are your overshooting tops on your cumulonimbus clouds. Strong updraft going up there, hitting that top of that layer, hitting a stable layer. It's really not stable, but it's not stable or unstable, because there's no temperature decrease or increase with height, but you can push into that layer. You can't push past it, because now you get into the stratosphere. Now you have temperature increase with height, and that caps everything. So you're not even thinking about going above that level. So overshooting tops, the only reason you need to think about the tropopause. That's your tropopause. That is the thunderstorm goes up, hits the tropopause. All that moisture goes up there, hits the tropopause. You got your overshooting tops from the updraft. And then you have the wind at that layer pushing up horizontally, and that's your cirrus blow off that creates the anvil over that cumulonimbus cloud, that thunderstorm. Stratosphere, layer above the troposphere, temperature remains constant or increases with height. It's a stable layer. Extends from above the tropopause to the stratopause. The height about 30 miles. Temperature increase with height is caused by the absorption of incoming solar radiation. And nacreous clouds, known as mother of pearl, can occur in polar regions. So that's that lower thickness of the atmosphere in the polar regions. So you can see those nacreous clouds. It's a stable cloud. There's really not much to those. No weather occurs out of those clouds anyway. So, planetary boundary layer is part of the atmosphere where the friction from the Earth's surface affects air motion. Top of the boundary layer is around 2,300 feet, but is lower over oceans and higher over mountains, because you have friction lower in the oceans and higher in the mountains. So your friction is going to go up all the way up to the mountains until you get above that. There's your planetary boundary layer until you get up past that to the free atmosphere. Now, higher wind speed will increase the height of the boundary layer due to turbulence and mixing. So it can push that boundary layer up, and you get that turbulence that creates a friction and creates eddy waves, and they will actually slow and back winds and create that basically just a friction. So you're not in the free atmosphere yet. Free atmosphere is a layer above the atmosphere. Layer of the atmosphere above the boundary layer, around 3,000 feet above mean sea level, where the wind is largely within geostrophic balance. So now we're talking about the winds are in geostrophic balance was pressure gradient force. In this case, it'd be 3,000 feet, so it'd be pressure contour gradient force and Coriolis force are in balance with each other. So you pretty much have a straight line of wind. Global circulation. Another important factor. Now, these are found to not impact weather as much as it was initially thought, but it gives you an idea of where the jet streams form and your subtropical highs and your Aleutian lows. Your subtropical or your, I want to say, call the Aleutian low, semi-permanent high and low pressure systems. So just semi-permanent systems that are basically permanent high, low, and pressure systems that migrate north to south depending on the seasons, and stay kind of in their general area, but they're always there. So the 3-cell model is a Hadley Cell, Ferrel Cell, and Polar Cell. Not sure if I did a picture on this either, but okay, the Hadley Cell, heat-driven circulation that originates at the equator. So we'll probably draw something up here in a minute. Air rises and flows toward the poles. Coriolis force deflects the air to the right in the northern hemisphere, where it accumulates in subtropical latitudes, resulting in a band of sinking air approximately 30 degrees latitude called subtropical high. Prevailing winds move from northeast to southwest, also known as trade winds or tropical easterlies. Okay, let me get a whiteboard up here and we can try something. Heat from the equator, so the sun comes in pretty much right at the equator. That's why it's the hottest. Heat rises off the equator, hits the tropopause, and then you got upward vertical motion. Hits a tropopause, got upper level divergence, goes toward the poles. It really doesn't have any other direction to go except toward the poles. And then up to about 30 degrees latitude. So there's 30, there's 60, of course there's 90, up to about 30. Now your prevailing winds are northeast to southwest. In the northern hemisphere. You're pretty much going to go southeast to northwest in the southern hemisphere. These are your trade winds. Alright, so the winds are going to be southeast to northwest, northeast to southwest. So these are your trade winds. That is where, along that tropical belt, is where you can start getting that rotation. That's why they start looking for these waves that form to create those hurricanes all along that belt all the way around the globe. So I got a whole chart on this thing I drew up once. So we have the Hadley Cell, Ferrel Cell, and the Polar Cell. So when we go toward the poles, we start getting downward vertical motion at the 30 degree mark. So we have upward vertical motion that hits the tropopause, comes over, got upper level convergence, downward vertical motion. So let me try to clear that up a little bit. So up, over, down, out, up, over here. So you're going to go that way. There's your upper level conversion. There's your downward vertical motion. There's your upward vertical motion. And it's going to go out. And then you're going to go back, up, a little bit off scale here, but maybe you get the drift. Let's keep reading on our Hadley Cell. So, alright, here's the globe. Here's the equator. The heat from the sun hits the equator, goes up. You got upward vertical motion. hits a tropopause, which is higher here than it is here. So you're going to kind of go like this. Remember, it's 4 miles and 11 miles. So 4 miles off the poles, 11 miles off of the equator, and then upward vertical motion goes out toward the poles. Okay, resulting in a band of sinking air approximately 30 degrees latitude. So we got 30 degrees here, 60 here, 90 here. Okay, so when we go upper level divergence, and then you'll create a downward vertical motion approximately 30 degrees. Well, that's kind of messy. Let's go back to our the Hadley. Let's go. We're on the Hadley cell. Okay. Ferrel Cell circulation that exists between 30 latitude and approximately 60 latitude. Surface air from the sinking region flows poleward, resulting in a band of prevailing winds that flow from southwest to northeast at the surface, and in the mid latitudes, also known as the prevailing westerlies. And then the polar cell exists between the North Pole and a belt at a roughly 60 degrees latitude. Cold air from the Arctic region flows south and is deflected by Coriolis force at about 60 degrees latitude, where it accumulates. The surface convergence in this region results in a rising motion, and then air rises and diverges aloft, flowing back to the poles. References polar easterlies and cold air outbreaks. Alright, that pretty much concludes this, but we're going to let's draw this thing out real quick. Like I said, these are pretty insignificant. What you're looking for mainly on this is the semi-permanent highs and lows. That's pretty much what you're going to get out of this. So here's the Earth, there's the equator. So obviously we're 0, 30, 60, 90 degrees. Okay, so upward vertical motion from the heat hits a tropopause, goes over, downward vertical motion at the 30. Outward flow to the 60, and then this cold air is pushing south, colliding with that air, creating upward vertical motion. All the way up, hits a tropopause, comes back around. Now you have convergence at the 30, right above the 30, upper level convergence, and that's going to cause that downward vertical motion. Now at the 30 degree mark, you're going to have high pressure because you have downward vertical motion on the Earth, so you have high pressure. Semi-permanent high. Alright, the Aleutian low, like I said, we had the United States and Alaska. There's California. You have a low pressure system here. That is the semi-permanent low off the United States. So you have upward vertical motion, you have low pressure across the 60, and then obviously high pressure at the 90 because of the cold air. So cold and so dense, you always got downward vertical motion. So down, down, up, that's creating your low. Go out, down, out, and up. And then over here back to this one. And then you got your upper level convergence. So then there's your high, there's your semi-permanent high at the 30, semi-permanent low at the 60. Now, are these always here? No, they do migrate north and south. When you're looking for, like off the Atlantic, you'll see the high pressure system. Off the Atlantic, wintertime, that thing will move north. through the fall, winter, because you'll get that low pressure all along the equator, those trade winds, and you'll start getting that rotation, so you can get a hurricane out of that moves up. And then depending on where that high is, if it's going to allow it to go around that high, unless it hits land, goes around the subtropical high, then you can get helps with the steering on the hurricane. But so the polar cell is high pressure at the poles. Now, polar cell exists between 0 and 60 degrees. From 60 down to 30 is the Ferrel Cell, and then from the 30 to the 0 is the Hadley Cell. So, like I said, it's a 3-cell theory. They found that they don't impact weather as significantly as they thought at first, but nevertheless, if you're looking at it from a semi-permanent high pressure systems, low pressure systems, stuff like that, then you can pretty much count those in. So just gives you an idea of where your highs and lows are. Alright, so that pretty much concludes this course for physics. We will get back into the next course. We'll cover weather observations on the next course. So if you like this class so far, give me a thumbs up, subscribe to my channel, and visit my website, Meteorology101.com, and get your head in the clouds.